Our next speaker knows a lot about innovation in the world of energy. Jon Wellinghoff is chairman of the Federal Energy Regulatory Commission. He has more than 34 years of experience in the field of energy. He was a member of the commission since 2006 and has been a chair since 2009. The philosophy that Chairman Wellinghoff brings to FERC can be summarized in 3 words: efficiency, technology, and innovation. In fact, as chairman, he created FERC's Office of Energy Policy and Innovation, which is responsible for investigating and promoting new efficient technologies and practices in energy sectors under FERC jurisdiction. He also co-chairs the Smart Response Collaborative, launched jointly by FERC and NARUC, and he is also, I might add, a big fan of electric cars. As the state of Nevada's first consumer advocate for customers of public utilities, Chairman Wellinghoff has also been and always been a strong spokesman for the customer, and he continues that role with FERC. It is a real honor to have the chairman here with us this afternoon. Please join me in welcoming Chairman Jon Wellinghoff.
Thank you, Tom, and I want to thank the Edison Foundation for having me here this afternoon. One of the first things I want to do is play for you one of my favorite commercials. Let's see if we can get that up.
I could while away the hours, conferring with the flowers, consulting with the rain. And my head I'd be scratching while my thoughts were busy hatching if I only had a brain.
Smart grid technology from GE will make the way we distribute electricity more efficient, simply by making it more intelligent.
If I only had a brain.
Now, I understand there may have been a few liability lawyers at the utilities that weren't real happy with that commercial. But that aside, I think it's so retro. I love it, of the idea of, if the grid only had a brain. Well, what I want to talk about today in the few minutes that I have is talk about how I've, at FERC, started to look at things differently. I think we all know that certainly Apple and the other phone manufacturers are now looking at these devices differently. This is not a phone anymore. This is something that can do multiple functions, that can do things all the way from carry your music and take pictures, but all the way down to provide data from your home to you with respect to your energy use, and at some time actually control your home energy uses as well. So the possibilities with these types of devices are very significant. But there are a whole array of other devices that we have to look at as something different than what we're used to looking at them as. For example, this is not a car. This is what people would call a Tesla electric vehicle, but because it is an electric vehicle, it has the opportunity to be something more than simply a mode of transportation. First of all, most cars today, interestingly enough, have more computing power in them than most residences or most buildings from a standpoint of operating the systems within them. And to use that computing power, we're going to see it more and more for various uses. But we need to look at these devices not simply as cars. Oracle, for example, is looking at electric vehicles as the next killer application to be capable of making customers want to share energy data with utilities. Ultimately, they'll do that if they can determine that they can get into smart contracts with utility companies or third-party providers and actually use these cars as something else. And let me show you how else they can be used. I know many of you who've seen my presentations have seen this slide. This is one of my favorite slides. This is a slide graphically depicting one car that's an electric car at the University of Delaware, where now they have 7 of these, that use those electric cars as transportation during the day, but in the evening, they plug in to charge. And while they're charging, which is the green line in this graph, going from virtually 0 to 100% charge, they're able to do something else. They're able to become a resource for the grid, an asset for the grid. And they do that by providing something called regulation service, which I think most of you know. I know a lot of you out here from the utility industry, but regulation service, briefly for those of you who may not know it, is the service necessary for the grid operator to have to maintain the stability and frequency of the grid at 60 hertz by ensuring that as loads on that grid go up and down, you have resources to match it. So you have to call on resources, and typically the grid operators would call on combustion turbine generators to match the resources of loads coming in to ensure that that frequency stays stable. So you signal a combustion turbine generator to go up as loads go up, you signal it to go down as loads go down. And these generators do it, but they don't do it very well in the sense that they don't do it as quickly as the loads come in and out because they're a little bit slower. There's some mass to those big technologies. So instead, if you use a different technology, like a battery or a flywheel, in this case a battery and electric car, you can in fact match that load signal for that regulation service very precisely, and that's what's being done here. The grid operator, PJM, which is the grid operator in the Mid-Atlantic area from New Jersey to Chicago, is sending a signal to this one car at the University of Delaware, which is the same signal that it would send to a generator, an AGC, automatic generator control signal, that this car has the microelectronics in it to receive that signal and respond back. So it, in fact, gets the blue regulation signal that you see in this graph, and it responds back with the red response, providing regulation service back to the grid. And it does it precisely in microseconds, as opposed to a combustion turbine that does it in a matter of a minute or so. In doing that, it can provide this service more efficiently than the traditional way the service is provided. It can provide it cheaper, it can provide it more effectively. And here's the good part for the consumer can get paid to provide this service to the grid. So right now, these 7 cars at the University of Delaware are each getting paid somewhere in the neighborhood of $7 to $10 per day per car to provide these services to the grid at night as they charge. And again, it's happening as they charge the car. So there's no conflict between what the consumer needs to do with that vehicle as a transportation device and the grid using it as a resource asset to stabilize the grid and ensure that regulation services can be provided. And regulation services are something you need 24 hours a day, 7 days a week, and you're going to need more and more of it the more wind and other variable resources you put on the grid. So this is a way that ultimately the consumer and the grid can come together by using things that we don't think of as a new asset for the grid. Here's another possible new asset for the grid. This is not an office building. What this is actually the headquarters of the company Schneider Electric outside of Paris, called Le Hive, recently built. The average electric consumption for an office building in Paris is 400 kilowatt hours per square meter per year. By 2030, the European Union wants that driven down to 50 kilowatt hours per square meter per year. Le Hive is in fact leading by example. It's reduced its energy consumption by more than 50% in less than a year, and it currently has a consumption level of 65 kilowatt hours per square meter per year, and by the end of the year, they believe that they will be down to 50. So how do they do this? Well, each employee in the building has an employee badge, like I do at FERC, like most of you do in your different companies and enterprises. And on that badge is a little IR chip that communicates with all of the different systems in the building, with the HVAC system, with the lighting system, with any system that the employee comes in contact with. So the employee then going into their office, all of the employee systems that they need to work with, the lighting and the HVAC, et cetera, are set to where the employee needs them to be to use that particular part of the facility. And so it automatically comes up as the employee goes in. Employee leaves, it automatically goes down. The building knows where the employee is within the building, and as such, all the systems within the building can be adapted and utilized in a way that they only are at that level necessary to provide the employee comfort and the employee services that they need to do their job. If the employee is not there, they don't have them anymore. So these buildings are very interactive from a standpoint of using them internally, and we can make them interactive externally to the grid as well in ways like this. Here's a graph of the locational marginal prices in PJM during the summer of 2006 in 1 week of August of 2006, which was the absolute peak time. During that peak time, PJM called upon its demand response resources, were buildings similar to the office building I showed that are actually doing things like lowering their loads based upon signals coming in from PJM. And in doing so, they were able to save over $200 million a year in 1 year, in 1 week, excuse me, $200 million a week in this 1 week of this one August period by reducing loads below that peak period of what it would have been otherwise. And the result was reducing their locational marginal prices significantly. So as a result, if we take this out over the entire country, we can look at a study done by Rattle Group that indicates that as in 20-year period, we could save as much as $31 billion overall by putting these kinds of controls in buildings to allow those buildings to participate in the grid as a grid asset, utilizing demand response. So we have an opportunity here, again, to look at a building no longer as simply something used for the occupants, used for the services, and used for the companies that occupy and own those structures, but used also as a grid asset for a purpose to stabilize and reduce grid prices. This is a house. Not your typical house, I'll admit. It is actually a smart home at the Museum of Science and Industry in Chicago. It has a sophisticated automation system that allows homeowners to operate home temperatures, lighting, entertainment features, etc., all on touch screens. It has an energy monitoring tracking system, and it tracks in real time the amount of energy that's generated. It's actually a net zero home, so it generates as much energy as it needs from the home's solar film on its windows and also solar generators it has embedded into its glass areas, and also a 40-foot wind turbine. It also can track energy consumption for the homeowners and feed that to the internet and associate that with pricing on the internet as well. So ultimately, it allows the consumer to do things that can integrate energy uses by the home with the grid. So ultimately, we're going to have, again, smartphones that have GPSs in them. Smartphone is going to know where you are because it's where you're with the phone, and your home's going to know where your smartphone is. So ultimately, your home's going to know where you are. So as you walk out the door, like the Hive office building, it's going to be able to, at your choice, shut down uses in your house that you will no longer need because you're no longer there. You're away from the house. As you come back, it's going to know how close you are to the house. You get 10 miles away, 5 miles away, 3 miles away. It's going to start up systems inside the house. It'll start up air conditioning. It's a hot day in August. Start up heating if necessary. Start up systems that may be systems that you would want to start in that house. And at the same time, it'll also be able to control your energy usage again for the grid, to interact for the grid in an interactive way. So all of these things, I think, will be possible. Let me show you an example of that, of something that I'm doing right now. This is a graph of my house. I have these systems installed in my house where I actually can see and have this data transmitted to me on the internet. The red line on the top is the total kilowatt hour usage that I'm using at any one period of time. This is in real time on a minute-by-minute basis, and I get this data transmitted to me on a minute-by-minute basis. The lower lines in different colors show me different usages in the house. So the one green, lighter green line that's going sort of up and down across the graph, that's actually my furnace blower motor during a winter period. This was in the evening from 10 p.m. to 11 p.m., showing that furnace coming on and off. The straight green line across the top above that is basically my family room usages, which is my TV and the lights in the family room, so I'm watching TV. You can all see when I went to bed. I went to bed about 10:50 there that evening because that all shut off. The lower blue line is my refrigerator compressor coming on. The purple line is my sump pump because I live down by Sibley Hospital here in D.C., and you live in an area where you're constantly pumping out water because you've got all this water moving underground. So I've got multiple uses here, but ultimately, once we have this data, now it's time for the consumer, for the utility, for third-party aggregators to figure out what to do with the data. How do you make this data useful? How do you make this data something that ultimately the utilities and the grid system can use to their benefit? For example, is there any reason that my sump pump has to come on the same time my furnace blower comes on? No. So if you can figure out how to disaggregate these uses, we can reduce peaks, we can reduce the overall impact on the system, and we can reduce costs for everybody. So I think this is the promise of the future of electricity. I think the future is here. We need to, however, ensure that we can enable it, and that's what we're trying to do at FERC. We're trying to enable it through a number of initiatives, and we think the best way to enable it is competition, competition, competition. I think we ultimately need to put competitive structures in place in the wholesale electric markets to ensure that those structures can enable utilities and other third parties to play in those markets and to have the ability to get the value for these products that can come from assets like automobiles, like office buildings, and like homes to make everybody's energy costs lower. Thank you all. Appreciate it very much.